So now we're going to talk about conductors and insulators. Conductors allow charges to flow freely within their interiors. So this means essentially the conductors don't impede the flow of electricity. The reason a conductor is able to do this is because the valence electrons in the atoms of a conductor are not tightly bound to the atom, and they tend to be shared by the other nuclei within that material. Insulators, on the other hand, do not allow the free flow of electrical charge in their interior. This means that if you have a charge in an insulator, it's pretty much going to stay where it is because it's not easy for it to move from one location on the insulator to another. A big factor in this is the fact that the valence electrons are more tightly bound to the atoms and molecules which make up the insulator. So when you place charges on a conductor, because they're allowed to move freely, and like charges repel, that charge is going to try and spread itself out as smoothly and uniformly across the surface of the conductor as it can. If you have anywhere where charges are bunched up, they're going to push each other away until they're spread out as far as possible. So in this image here, you have a before picture where some positive charges are placed on the right-hand side of a conducting sphere. And because those positive charges repel, that positive charge is going to spread itself out across the sphere and try to be as uniform as possible. So the general principle is that when you're talking about a conductor, the charge always distributes itself across the surface and it tries to be as uniform as it can. For an insulator, because charges can't flow in through the interior or across the surface of an insulator, when you place charges on the surface, they just stay there. So if we had the same situation but with an insulated sphere, the charges would just stay where you put them, and so in this case we put some positive charges on the right-hand side of the sphere, and they stay on the right-hand side of the sphere. Polarization is an effect that happens in the presence of external charges. And so essentially what polarization is that in the presence of a charged particle, there will be a separation of charges in a neutral object. So in this picture here on the left, we have this rectangle which has positive charges and negative charges inside of it. And you can think of the positive charges as being the protons and the negative charges as being electrons. We bring in an external positively charged object to put it on the left of that rectangle. Because we're looking at a conductor, which would be the most extreme case of polarization, the negative charges all flow to the left of the rectangle to get as close to that external positive charge as possible. And they leave behind the positive protons on the right-hand side. So we think of this as a separation of charges within the rectangle, and it's induced in the sense that it's caused by an external object, that is this charged sphere on the left. Polarized objects are always going to be attracted to the charged object that caused the polarization. The reason for that is, if you look at this picture at the bottom, the picture is a little bit backwards, so let me fix that. The reason for that is that the negative charges get close to the external charge, and the positive charges are far away. So you should understand that this positive charge exerts an attractive force on these negative charges. However, this positive charge exerts a repulsive force on these positive charges. So part of the polarized object is attracted, and the other part is repelled. But the part that is attracted is closer. And because it's closer, the electrical force is greater. Remember, that's one of the principles we learned about the electrical force, is that the effect is stronger the closer the charged particles are. So polarization creates a situation where the piece of the object that is attracted to the external charge is closer to the external charge, and therefore the force of attraction is greater than the force of repulsion, leading to a net force which is overall attractive. In principle, any object can be polarized, even insulators. But the magnitude of that polarization is weaker the more the material inhibits the flow of charges. Obviously, the more charges can flow within a material, the greater the polarization will be when an external charge is present. Your fingers, for instance, or just a human body in general, because you're mostly a electrolytic solution, you have a lot of moisture inside your body, and it's basically there's a lot of dissolved ions in the form of salts, and so what you'll find is that if you put an external charge near your finger will become easily polarized, and it'll be able to attract both positively charged and negatively charged objects. Conductors are more strongly polarized than insulators, and I had already mentioned that. Basically, because charge can flow more easily, the effect of the polarization can become greater. So on the left, I have a schematic of what a polarized conductor might look like. We have a positively charged external particle. We have a conductor in which, I've got all of my charges are backwards, I apologize. So let me fix this right here. So in this case, all the negatives are close to the positive charge. All the positives are left behind on the other side. In the case of an insulator, you'll have a similar effect, but it'll be much weaker, where perhaps the electron orbitals just get a little bit deformed, where the electrons tend to hang out on the side of the external charge. So in the insulator, you can still see the negatives are trying to get closer to the positive, external positive charge, but the effect just isn't as significant or dramatic. Okay. You can charge objects by induction if they can be polarized, and this is something that applies more to conductors than insulators. And essentially this is how you do it. You take two conductors and put them in contact with each other. And since they're in contact, charges will be able to flow freely between them. Then you bring an external charge, such as this positively charged sphere in part B. And when you bring that charge, the combined system of the two conductors becomes polarized, with negative charges tending to be in the left-hand conductor and positive charges tending to be in the right-hand conductor. Then you separate the conductors from each other, and now the charges no longer have the ability to recombine. You take away the external positive charge, it's now gone, and now that it's gone, you have two conductors, one which is positively charged and one which is negatively charged. And unless those conductors are brought back into contact, they will not have the ability to restore the charges to where they came from. So now you have two charged objects, one positively charged and one negatively charged, and the amount of charge is going to be equal. So if the positively charged conductor has a charge of plus Q, then the negatively charged conductor is going to have an exactly equal amount of charge, negative Q.